Hello, everyone. We will get the session starts. You made it in the last day of Kai at 9 a.m. So proud of you all. So we will start the session steering and evaluating generative AI. We have 6 papers in this session and 2 honorable mentions. So let's start the first paper. Let's welcome Agathe, postdoc from Microsoft Research. She will present the paper, A Framework to Characterize the Reporting on Generative AI Use. And let's welcome the speaker.
Thanks. Hi, everyone. So in this project, we looked into reports about the use of generative AI. And this isn't about really cataloging uses, but it's more about making explicit the assumptions and reporting choices in current industry documents and studies that shape the narrative about generative AI use. And this is work that I've been conducting during my postdoc at Microsoft with Varun, who is right here from CITP, Solon Blodgett, Aylin Caliskan, and Solon Barocas. And so why are we looking at generative AI use? So for predictive AI, use might not be really a question to investigate because the purpose of the model is built in. By design, it's limited by the inputs and outputs of the systems. But unlike predictive AI, generative AI models are general purpose and open-ended, so they can be used in many contexts and with many different kinds of interactions. So if we don't study use, we don't know what the users are actually doing with these models. And there are many stakeholders who might want to know about use. For instance, developers, to make sure that the models they are building function for their expected use, but also evaluation conductors to make sure that their evaluations are ecologically valid, or also governance practitioners, for instance, by knowing use, they can understand better the impacts of their models, and they can develop governance policies, structures, usage policies, etc. In practice, there are already long-standing efforts across academia, civil society, and government that have urged for greater transparency surrounding generative AI. So these goals often build on system cards, and system cards primarily tell us about potential use, so capabilities that tell us about potential use. But more recently, scholars have also explicitly called for more explicit information about actual use. And this is now provided across various kinds of documents, for instance, papers and technical reports, but also marketing materials from GenAI providers, as well as usage policies. So ultimately, we're starting to swim in documentation that talks more or less directly about generative AI use already. And that's why we're arguing that we need a meta-study about use. So the information is currently fragmented across many documents, so it's hard to tell what our knowledge gaps are currently. And the information comes from various different sources with different kinds of incentives. And all of this craft the narrative about use, so we better understand the limitations as well of this documentation. For instance, lots of use data might be ambiguous and might also lack methodological rigor, for instance, going from AI capability to use information. And so concretely, in our work, we asked 2 research questions. The first one is, what are all the possible ways to report about use? And we answered it by developing a framework that helps researchers, practitioners, and policymakers to reason about use claims. And the second question is, how do major GenAI providers actually report on use today, and what's the narrative that they are building? To answer the first research question, we conducted an integrative review. So we looked into 40 documents that are reporting about use, developed an initial framework that we revised, looking at prior literature that talks about technology use more generally. And this is what our framework looks like. So there are 3 major components. The first one talks about usage information. So we distinguish between information reported in the documents that refers to the context of use. For instance, who uses a system, which system, where, and when. And we also have questions that refer to the interaction information, so use interaction. So what do the users use the systems for, why, and how? We also distinguished between temporalities. So the use claims might refer to actual current use, observed use, potential use based on especially capabilities, or projected use if the capabilities would develop in the future. The second part of our framework is the study design. With the study design, we distinguish the various kinds of methods that are used to collect data about use. Especially, there are methods that are focusing more on models, such as benchmark evaluations and red teaming. And there are other methods that are looking directly into the user interactions, so log analysis, user studies, or surveys. And in our framework, we have additional dimensions to further categorize the methodologies employed to learn about use. And these are dimensions useful to reflect about the methodological rigor of the information. The last component of our framework is the study population. And the study population specifies what generative AI systems are studied in the documents that are reporting about use, and what's the scope of the users who are also represented in the data that has been collected. And it's interesting to note that the study population within the data might actually differ from the information that is reported in the documents later on. To then apply our framework, we collected 111 documents from major generative AI providers. We sorted quotes that are talking about use from these documents, took memos while conducting this exercise, and did some thematic analysis to identify various patterns of reporting about use across the documents. There are many findings in the paper, so I will just mention a few of them now. Especially, we actually identified that the types of information covered about use is pretty broad across the documents. Almost all of the use questions are always covered by these companies. And if we look at the answers to the questions, the use questions, these answers can be really rich as well. So for instance, here I'm showing answers to the who question, who uses generative AI, and we can find a wide diversity of these answers. So people talk about the professional role of the users, their socio-demographic backgrounds, whether they are early or late adopters, what kind of organizations they are working for as well, and many other information. Looking at the study designs, we also identified quite a wide diversity of study designs. More than 9 interaction-focused methods are employed, and more than 6 model-focused methods as well, which helps explain the diversity of the use questions and use answers given. However, we also identified many gaps in the reporting. Some of the use questions are more or less poorly answered, especially the when and where, for which we don't have much information. Looking at the study population, there are also scopes that are more or less well represented. For instance, users who are working in specific sectors are typically not mentioned, such as for the military. There are also various kinds of documents, use contexts that are covered. Lots of documents talk about adversarial use, but very few documents talk about an unintentional misuse by regular users, for instance. And if we look at the temporality of the use information, it's also quite unbalanced. For instance, for the interaction-related information, a lot of the information is covering potential use, but we have very few or less information covering actual use, and even less for projected use. And looking at the study designs in comparison to the actual information reported, there are also often misalignments. For instance, some studies collect data about multiple models and accurately report that use differs across these models. But other studies collect data about specific models, and the claims sound like they are referring to any kind of model. There are also studies that overinterpret the data. For instance, studies that refer or look at logs, but also talk about the user intent that is not necessarily contained in the logs. And we also found very ambiguous statements. For instance, this one, which tells us that there are millions of users, but without characterizing what is a user. For instance, how often they should have used the system to be considered and counted as a user in the document. And other similar quotes, for instance, that are hard to sort into the framework into any of the use questions because they are quite vague. And these are like different quotes that shape the narrative about use and especially contribute to having an image of omniscience of these systems, which might more or less be valid. So what are the implications of these studies? This study, we have multiple ones, especially for HCI researchers. We are identifying knowledge gaps in terms of the use information. We're encouraging researchers to look into which methods, HCI methods they could use to further study use. And because there are so many kinds of use informations that could be reported, so across the use questions and the temporalities, we also think that HCI researchers are well placed to conduct need-finding studies and try better understand which information is worth sharing to which kinds of stakeholders later. For policymakers, our study tries to surface what kind of narrative is pushed towards them around generative AI use. And we think they can also use the framework to better craft transparency obligations for future reports about use. And for practitioners, they can leverage our framework both as a guiding tool to craft studies about use and as a reflexivity tool later on to reflect about the documents they are authoring. So that was all, and thank you for your attention.
Thank you so much for the great talk. Any questions from the audience? And we'll have student volunteer help pass the mic. I will ask a question first. So in your slides 14, would you mind go back? I'm curious, there's two blocks, is orange from Google and Meta for the when question. What does that mean?
Yeah, so we collected around 15 to 20 documents per organization. And then we sorted the documents or the quotes from documents to see which questions they are covering or not. And so Google and Meta didn't have any document, or at least we didn't find any document that were reporting about the when question at all.
That's interesting. Any other questions from the audience? Oh, thank you so much. We'll have our second speaker come to set up. And let's give another round of applause. And then we'll have Anna Martin-Boyle from the University of Minnesota to present her paper, An Expert Schema for Evaluating Large Language Model Errors in Scholarly Question Answering Systems.
Hi, everyone. Thank you for being here. I'm here on behalf of my collaborators from NASA Langley Research Center, as well as my lab group Lens, to present an expert schema for evaluating LLM answers to scholarly questions. This is a problem we're all familiar with. There's an information bottleneck that we as researchers have to deal with as the growth rate of scientific literature becomes exponential. Multiple tools have cropped up to help deal with this issue, but they're not without flaw. They make many different kinds of errors and have contributed to even scientific malpractice. A big problem is that, how do we know we can trust these tools when we use them? Evaluating LLMs for scholarly question answering is a difficult problem. For one thing, it is open-ended. When you ask a question about a paper, the scholarly answer doesn't have a single ground truth, and multiple valid interpretations can coexist. It's also context dependent based on the user's needs. Furthermore, end users can't know what they don't know. Subtle errors look convincing when you lack the expertise to spot them. And automated metrics miss domain-specific nuance and don't reflect how experts actually assess outputs. Automated metrics are certainly lagging and really not capable of dealing with this issue. We present an expert evaluation of LLM outputs for scholarly question and answering, where we define expert as an actual author of the paper being questioned. We then show a schema of LLM errors in scholarly question answering, as well as expert evaluation strategies and priorities. So, how should we evaluate scholarly question answering? There are a couple ways that you can evaluate question answering, and they are broken down by Rodriguez and Boyd-Graeber into two categories. The Manchester paradigm says that a good QA system demonstrates actual understanding. The Alan-Turing test falls under this category. The Cranfield paradigm says that a good QA system answers the questions that users ask, so it's more user-facing. So the central question with Cranfield isn't if the LLM is good as a whole, but if its outputs meet the user's needs. However, this doesn't help us understand the full capabilities, and this can only be evaluated by an expert. Here's an example of why it's critical to have expert paper authors help evaluate systems. An expert asked, "How was the testing process conducted?" The LLM then described one test correctly, but skipped an earlier test where the most important lessons came from. I, as the model developer, coded the issue as simply lacking detail, but our domain expert coded it as a chronological misunderstanding because they had the knowledge of what's in the paper to know that there was an ordering issue. This was not something that was easy for me to find. This is how we built the schema. In phase 1, experts engaged in scholarly question answering with an LLM. 2 experts wrote questions about 9 papers that they had authored, resulting in 68 question-answer pairs, and we generated those answers using a RAG system based on Mixtral. We had a 3rd expert who could kind of verify the codes that these 2 other experts wrote. And these are 3 of our co-authors on this paper. They then helped us with thematic analysis of those question and answer pairs. We did an open and axial coding that resulted in 7 categories with 20 patterns. We then needed to validate that schema, so we had an additional 10 new experts engage in question answering on their own papers. And we did a contextual inquiry with the Think Aloud protocol. We then after they gave a free response to the question-answer pairs, we then asked them to apply the schema to the answers that they were seeing. We then coded those Think Aloud transcripts as well. So I'll now present the schema of LLM errors in scholarly question answering systems. This schema included incorrect answers, hallucinations, which are also incorrect but prevalent enough to deserve their own category, incomplete answers, issues with misinterpretation of the question being asked, synthesis issues, formatting issues, and system failures. First, I'm going to show you an example of a hallucination in this context. Our expert asked, "What is BVI noise and how does the compact assumption influence it?" The LLM output expanded the acronym improperly. This led to it building an internally consistent but completely wrong explanation. The domain expert obviously was easy to catch this, as it's in their domain of expertise, and it's also about their own paper, so they know what's supposed to be in it. A non-expert might find this answer convincing if they're not paying attention, as it reads like a coherent technical explanation. Next, I'll show you an example of a question interpretation error. The expert asked, "How are diffractive optics made?" The LLM then described properties and applications, And the expert commented that almost everything there was true, but none of it is actually how they're made. It's not wrong, but it's not the question that was asked. So the LLM redirected the question. We also gained insights into how experts evaluate scholarly answers to their questions. They naturally identified misinterpretation of paper content, which makes sense because they are the experts in those papers. They also were able to identify when the LLM missed the main point of the paper, as well as partially incorrect details and verbosity and poor focus. However, surprisingly, they missed citation hallucinations. In the first hour of our interview, where they responded freely without scaffolding, only one expert noticed a fabricated citation. After presenting them with our schema, 8 total were able to then identify hallucinated citations. But only one expert was proactive in checking citation accuracy. Finally, I'll tell you about some of their evaluation strategies. They did systematic testing. This participant stated that he tried to make a part of it easy and part of it really hard, swinging for the fences to see if it can understand. They also did value-based assessment. They appreciated when the LLM was willing to admit not being able to, say, read a figure or answer a question in any way, and described that as a virtuous response. They also performed meta-evaluation. Multiple experts observed that it might answer the question differently than they were expecting, but acknowledged that it could have been because of the way that they asked it. They said that if they were to continue evaluating the system, they would have revised their prompt a few ways to probe how it was really answering the question. We conclude with some implications for scholarly AI systems. We suggest opportunities for hybrid evaluation. Some errors are more automatable. For example, incorrect citations can be easily detected through, say, regular expression matching, cosine similarity, RAG systems. Others resist automation, so highly specific technical content is included in this, as well as synthesis. LLMs tend to synthesize very poorly, and the way you synthesize multiple sources is informed by, say, the goal that you have in writing your related work section. We also suggest an opportunity for personalized adaptive interfaces. Experts varied in which errors they caught and found the full inventory fatiguing. Progressive disclosure based on individual evaluation patterns could help with this. Thanks very much. You can find the paper using this QR code, and I'm happy to take any questions.
Thank you so much, Anna. Any questions?
Thank you for your nice presentation. Karthik Ramani from Purdue. It seems like if others want to develop a similar system, they have to go through this process, and it will be very tedious. And yet you're trying to bring more constraints into the nature of answers, but you want to still be flexible enough to allow for variation, right? So I don't know if you have any thoughts on both repeating these types of things in a more easier manner, but still allowing the user to be in control of how the system works.
Yeah, absolutely. And a quick comment on like why we developed this in this way. This was developed at NASA, and like government agencies tend to want to like have these kinds of systematic taxonomies or guidelines for when they're assessing technical or technological systems. And so in this setting, it was a very like culturally appropriate way to go about it. But not all settings are like that, certainly. I believe that there could be ways of scaffolding this kind of metacognitive process for any expert who is maybe evaluating a system. Certainly, in this case, we used paper authors themselves And if I'm a scientist, and if I want to evaluate a scholarly question answering system, I could then probe it using my own papers. But there might also be opportunities for crowdsourcing this kind of evaluation as well. Thank you.
Thank you so much. And let's welcome our next presentation, and it's also the first honorable mention in this session. So we will have Yehang to present this paper. She is not the author on this paper, but kindly will present for her collaborator on behalf of the course, speaking SemTabla, a human-in-the-loop framework for semantic enrichment and the validation of data tables. So we'll save the time for questions, and if you have questions, just contact the authors afterwards. Thank you so much, and let's welcome the speaker.
Okay, hello everyone. My name is Yehang. Today I'll be presenting this work on behalf of the authors who are unfortunately unable to attend the conference. And today we'll introduce an interactive system that uses a human-in-the-loop approach to extract clear and interpretable meaning from tabular data. This work is a collaborative effort from the team of Nanjing University. This talk is structured into 3 main parts. First, we'll discuss our motivation and the findings from a pilot study. Based on that, we'll introduce our system, SemTabla. Finally, we'll walk through the evaluation results. Data tables are the foundation of organizing information across every industry, from finance to healthcare. With the rise of AI, we expected large language models to act as a smart bridge between humans and structured data, making querying and analysis much more intuitive. However, the standard row and column format often misses the bigger picture. Critical business context is usually missing from the schema. For instance, the model can't tell if a balance column should actually be added up, or how 2 tables might be secretly linked. Without this context, even the best LLM will struggle and produce answers that don't fit real-world logic. We interviewed 5 experienced data practitioners to understand the real-world challenges with table semantics. The reviews followed their daily workflows and focused on 3 aspects. First, common table types and semantic ambiguity, including examples of misleading or incomplete field names. Second, strategies for interpreting table semantics, such as how they explore new tables and validate assumptions using SQL. Third, the impact on LLM applications, especially how semantic gaps can lead to failures and what additional information could improve model performance. The interviews reveal 3 key findings. First, a multi-level framework is essential. This includes field meanings, table hierarchies, and relationships. Second, query records is the most effective way to understand semantics. Experts don't just glance at the first 100 rows. They use an iterative approach. For example, an expert might start with select from the table limit 10 just to get a feel. But then, they actively construct specific SQL queries to verify hypotheses. They might run select count where status equals to pending to test if a status column behaves as expected. Third, missing semantics cripple intelligent applications. As one expert bluntly stated, it's fair to say that missing semantic information is currently the biggest factors affecting the accuracy of natural language query systems. We can't expect models to accomplish what even human experts struggle with. To address these challenges, we built SemTabla. It's a semi-automated framework to understanding tables. Our key contributions include a hierarchical framework that combines metadata and data-driven profiling, an efficient sampling method for large-scale data, and an interactive interface that lets users validate and refine the extracted features. We also created an evaluation framework to test both usability and performance in question answering. Users begin by importing a data table via the upload button. Once uploaded, the system then initializes and displays the table's basic metadata. The interface then provides 2 semantic modules to help users understand their tables: semantic enrichment and semantic validation. The semantic enrichment module guides users through the automated steps to extract semantic features. It progressively reviews field-level semantics, table relationships, column dependencies, and finally summarizes semantic labels and table type. Within the semantic validation module, users can click any semantic feature to view both conforming and non-conforming data samples, verifying the analysis results of the system. Users can refine the status and trigger revalidation on the updated data. The semantic enrichment module extracted and summarized the most critical semantic labels from the structured tables to facilitate table understanding. The identification of semantic labels follows the findings from the pilot study and proceeds according to a four-level analytical framework, providing a comprehensive and structured summarization of the semantic information in data tables. First, it extracts features at multiple levels, looking at individual columns, relationships inside the table as a whole, and finally, connections to other tables. Next, it detects the table type using these features. The system assigns semantic labels and uses a decision tree to classify the table. For example, determine if it is a transaction table or a dimension table. To handle large datasets efficiently, we use a representative sampling loop. It works like this. We sample data, detect a feature like whether one field is a primary key, and then search for counterexamples. If we found an counterexample, we add it to the sample and run the detection again. This ensures we catch critical low-frequency patterns without scanning the entire massive table. The semantic validation module allows users to verify and correct results. When users click on any extracted feature, the system queries the original table and returns both supporting examples and counterexamples. Positive matches are highlighted in green and contradictions are shown in red. Each sample includes a clear description of the condition being tested and the SQL query used to find it. The actual data records are then displayed in the sample data table for easy inspection. Following validation, users can further refine the identified results. For instance, one user discovered that two columns in the table had incorrect data types and cracked them to the proper types. After the modifications, the system performed a new round of iterative detection and optimization, and the type of the table had also been adjusted to a transaction table. We conducted a user study with 18 participants to evaluate SemTabla's usability and effectiveness. We compared it with two baselines, one using an SQL editor for manual exploration and another providing automated semantic enrichment with visual verification. The study used two schemas from the BERT dataset, covering both simple and more complex databases. We evaluated 6 metrics, including usability, mental effort, accuracy, and task time. Overall, the SemTabla was rated higher in ease of use, lower mental effort, and better accuracy. Participants also completed verification tasks faster, showing improved efficiency. We also tested system performance on large-scale data. Across datasets with up to 100 columns and 1.6 million rows, detection latency remained low. Even as data size increased, the runtime for tasks like key detection showed a steady but manageable upward trend. The ablation study evaluates our semantic enrichment using the BERT benchmark. We compare standard prompts with SemTabla enhanced prompts and observe consistent gains across models. Qianwen 3 Plus improves from 36% to 45%, and DeepSeek V3 from 43% to 51%. We also analyze performance by question type. The largest improvements appear in multi-table queries, where join reasoning is critical, with additional gains in time-related and aggregation questions. On the right is the example. For a query about low red blood cell counts, semantic enrichment helps the model correctly link the condition to the lab table, avoiding confusion with similarity named columns. In conclusion, we want to highlight two feature directions. First, scalability. We plan to move from local file uploads to a distributed database backend to support truly big data scenarios. Second, we want to incorporate data development scripts. While analyzing data records is powerful, adding insights from SQL transformation logic will give an even deeper understanding for data lineage and column calculations. Thank you very much for listening. If you have any questions or are interested in this work, feel free to contact with the authors by email.
Thank you so much, Yechen. And let's welcome for the next presenter for our next presentation about the labs, automating hypothesis-driven statistical analysis of public survey using large language models. And we'll present by Jaehoon Kim from Hanyang University.
All right. Hello, everyone. I'm Jeong Kim from Hanyang University. Today, I'll be presenting labs automating hypothesis-driven statistical analysis of public survey using large language models. So this work was conducted in collaboration with Dayoung, Jeong, Beejin, Professor Han-Sung Kim, Professor Bo-Kwan Kim, and Professor Yangshi Khan. So I'd like to begin by providing some background. So public survey data is essential for understanding social dynamics in health, education, and beyond. And social scientists are actively using these data sets for academic research and public policy development. So how do social scientists actually analyze this data? It's a usually three-step process. So first, they formulate a theory-based hypothesis, and second, they operationalize abstract concepts into measurable variables. So finally, they apply statistical models to test them. So this process seems straightforward, but applying it to massive public data set is very challenging. So through iterative discussions with domain experts, we identify three key challenges and corresponding needs. So first, we observed cognitive overload from hundreds of inconsistently structured variables. And second, we found a lack of structured tools, making reproducible planning very difficult. And third, general purpose LMs are often too unpredictable, so researchers need reliable tools that operate under appropriate constraints. So this needs led us to formulate three design goals. So first, the system suggests candidate variables and explain why. Then researchers can easily review and modify them. And second, it provides a structured analysis plan, so users can work with the system to iteratively improve the plan. And third, we use a domain-bounded workflow, so this means the AI is limited to the specific research context. So this prevents random errors and make the tool trustworthy. So based on these design goals, we structured the system functionality into 4 steps aligned with a hypothesis testing procedure. So labs consists of a total of 9 LLM agents. So in step 1, operationalization, 4 agents work together to map abstract hypotheses to concrete survey variables, realizing design goal 1. And step 2, planning, it uses the data descriptor and analysis planner to structure the statistical methodology, realizing design goal 2. And step 3, execution, it employs the code generator and debugger to produce and debug analysis code. And then step 4, reporting, it generates comprehensive reports through the report composer, so the entire workflow is constrained within a domain-bounded pipeline, so it realizing design goal 3. Okay, so let me briefly demonstrate how the system operates. So in step one, firstly, the user inputs their hypothesis. So in this case, the user wanted to examine whether perception of fairness in job selection opportunities differ according to the level of education. So after this, reps automatically identifies appropriate variables. So users can review the variable recommended by reps in the selected variable window, as you can see. And then the education level variable was selected as the independent variable. And in addition, a variable regarding the perception of fairness in job selection was selected as the dependent variables, and while other variables such as age and gender were selected as control variables in this case. So crucially, the user maintains full control through the conceptual search space. So by using this method, the user can review, add, or drop variables. So as you can see here, the user requested to remove the age of variable. And then the user reviewed the updated variable lists again, and as there were no additional requests, so variable list was finalized, and as you can see here, age variable has been removed. So in step two, reps suggest a structured statistical plan, so users can review and update the plan through the analytical decision space. So in this example, the user requests to change the primary method to ordinal logistic regression. And then, as you can see here, the user successfully updated the plan to use a logistic regression instead of original method. And step 3 and 4 handle execution and reporting. So reps generate statistical analysis code with R and Python. So if an error occurs, so it automatically debug error. And then our final step, so once successful, it creates an analysis report with results such as p-value, effect size, and interpretation. So the hypothesis testing results in this case show the positive correlation between an individual's educational level and the perception of fair job selection opportunities. So in addition to this, the report provides analysis of control variable and interpretation. So to validate reps' technical soundness, we tested it against 5 textbook exercises for complex survey data. So reps produced identical results across all 5 exercises. And then next, we evaluated user experience. So here's the overall flow of our user study. So we employed the within subject design, where everyone experienced all 3 environments, the baseline, the general LLM, and reps. And we fully counterbalanced the order to prevent running effects. And then we measured usability with SUS, and cognitive workload with NASA TLX, and trust in AI with TXAI questionnaire. So finally, we conducted semi-structured interviews with all participants. So we conducted this 2-hour study with 12 social science researchers. So our results show that reps achieved significantly higher usability scores. So, and participants highlighted 2 key themes in here. So reps served as a collaborative tool that preserved the researchers' control, and reps raises the baseline of analysis quality. Overall, users mentioned reps positively compared to their previous experience using existing analysis tools. And for cognitive workload, reps showed substantial reductions compared to both environments, baseline and general purpose LLMs. So reps reduced the cost of explanatory analysis by making early analytical conditions visible. And also, reps enabled researchers to focus on conceptual decisions rather than tool management. And then these results suggest that automated tools like our reps can reduce the burden on researchers in research. So finally, regarding trust measured by TXAI, reps scored higher than the general purpose LM environment. So especially our participants P10 mentioned, reps explains exactly why it chooses certain variables or methods. They never felt like they were just blindly trusting the AI. Oh, sorry. So these results suggest that a controlled environment can increase user trust. Okay, so this led us to 3 design implications. First, we must make data processing steps visible to prevent novice researchers from losing critical data research skills. So the automation of tools can sometimes lead to uncritical acceptance of results. And second, analytical tools should integrate on-demand evidence to connect statistical choices directly to theoretical literature. And third, AI tools can incorporate cross-domain simulations to support diverse multidisciplinary interpretation. So finally, 2 important considerations. First, one thing is strict AI safety filters sometimes block regimen analysis of sensitive survey topics like mental health. So we need to better balance safety policies with research robustness. And then second one thing is transparency of research still relies on human ethics. So automating audit trails, as RAPS does, supports accountability but doesn't replace the researcher's ethical commitment. So for more details, please refer to our paper. Thank you for your listening.
Thank you so much, Jaehoon. Any questions from the audience?
Hi, thank you for the nice talk. Thomas from Carnegie Mellon University. My question is on the aspect of where your last takeaway, or one of your final takeaways around junior researchers who are still learning and perhaps developing some of these skills. In the instance where they are perhaps removing a variable, is there any sort of warning system of that variable might actually be quite important, and any sort of guardrails built into the system, or perhaps in future work for the system?
Actually, yeah, that's a good question. Actually, in our user study, some experts mentioned that especially novice researchers use our tools labs, so they can just trust over trust the AI system and just results. So I think we can just put some functions to our future study, just alert messages. If, for example, we can put this message, this decision influences your next steps, and then this is very important. So you must check all things in this steps like this. So and then other things we can consider in our future study.
Very cool. Thank you.
Okay, thank you.
Thank you so much, Jaehoon. And let's welcome our next presentation. The talk will be about preference-guided prompt optimization for text-to-image generation, presented by Zhipeng Li from UTH Zurich. Welcome the speaker.
Okay, thank you for introduction. Hello everyone, I'm Zhipeng Li from ETH Zurich, and today I'm presenting our paper, Preference-Guided Prompt Optimization for Text-to-Image Generation. I worked on this project together with Yichiliao and Christian Host. And first of all, let's have a look at how users generate images using our method. So at the beginning, the user may just have a very rough idea in their mind. And with the idea, the user only needs to provide a rough initial prompt, which might be missing details or incomplete. Then our method will generate a batch of candidates based on the initial prompt. The user just needs to observe these results and then simply select their preferred ones. With this selection, our method will infer the user's generation goal and refine the prompts automatically. And then generate a new batch of candidates, and the user still just needs to look at them and select their preferred ones. our method will keep refining the prompts and generating new results that are closer to what the user wants. And finally, in the third iteration, the user finds a satisfied result. And as you can see, it's quite similar to what they want at the very beginning. So let's take one step back and look at the initial idea. The user only provides a quite short and rough initial prompt. But after 3 iterations, our method infers what the user wants and refines the prompt into this complicated one. And this prompt generates an image that aligns with the user's generation goal. But such a complicated prompt is very difficult for the user to create themselves. There are 2 main reasons. First, the user cannot perfectly articulate their generation goal in the beginning. Instead, they may only have a general idea of the essential objects and a rough visual style. Second, even if they know what they want, they also don't know how to translate their ideas into effective prompts. So we perceive the process of getting the prompt that generates a desired image as a search in the huge prompt space, where the user always starts from a rough idea and gradually search for a better prompt, which is a typical trial and error process and requires a lot of iterations. So recently, HCI researchers have been trying to build interactive tools to support users refining their prompts. With these tools, users can better understand how the prompts affected the generation results. But users still need to write and refine the prompts by themselves. So it still heavily relies on human effort. And in machine learning field, there are also many papers focusing on automatic approaches to optimize the prompt. They optimize the prompts towards predefined numerical metrics, such as semantics, alignment, or aesthetics, which means they always make the prompts better in an overall perspective. But in reality, the quality of generation results are subjective, and there is no well-defined metrics to capture this. So in this paper, we introduce adaptive preferential prompt optimization, APPLE. It's an automatic prompt optimization method guided by users' preferential feedback on generation results. Like I introduced at the beginning, in our workflow, users don't need to read the prompts or manually refine them. They only need to provide their binary preferences on the generation results. And this means that when we are searching in a huge prompt space, the only information we know is the user's preference feedback, which is not very informative. The second thing is that the generation results are optimized towards users' individual preferences, which means we cannot leverage experiences from previous users or tasks. And the last but not the least thing is the users usually get their desired results in a few iterations, so we only have very little interaction data to learn from. Overall, this introduce significant challenge on how to exploit what we know about users' preferences and also how to explore the huge prompt space. To address these challenges, we propose our method, adaptive preferential prompt optimization, APPLE. It takes the user's preferred and non-preferred prompts as input and output a set of prompts that it optimizes for the inferred user preference. More specifically, our method includes 3 optimization strategies. The first one is retainment. With the user preference as input, it keeps the prompts that are preferred by the user in the previous iteration. This ensures that the quality of the generation results in the next iteration will not be worse than the previous one. This strategy only exploits what the user lacks. The second strategy is alignment. It compares each prompt from both the preferred ones and the non-preferred ones, and the comparison results are then summarized as a textual gradient, which is a text that describes the difference between these 2 sets of prompts. And then it applies this gradient on the non-preferred prompts to refine them. So this strategy exploits what we know about what the user likes and dislikes. And it also explores a bit around the preferred ones. The third strategy is expansion. It uses the concept of evolutionary algorithms, which means it first performs crossover on the preferred prompts. More specifically, it breaks the prompts into smaller parts and then recombines them to create new prompts. And then it performs a mutation on these new prompts. The mutation could be reordering words adding modifiers, or adjusting the sentence structure. So in this way, it creates new prompts that keep some part that the user may like, but also explore new directions. Okay, now we know we have the algorithm to optimize the prompts in one iteration. But after a few iterations, the optimized prompt will start to converge, which means it will be very similar to each other. This is good if the user is satisfied with the generation results, which means we find what they want. But what if they don't like the results and want to see something else? So we also include an adaptive policy, which in each iteration, it compares the retained prompts to the aligned prompts. And if they are very similar in semantics, then we will encourage the expansion strategy to explore entirely different visual styles, details, or wording. But if the retained and aligned prompts are not very similar, which means the optimization is not converging yet, then we limit expansion to more local changes, such as replacing a few descriptors. So by doing this, Apple enables the generation process quickly converge the user's preferences, while still can explore new directions and avoid getting stuck in local optima. We then conduct user study to evaluate our method. In our study, we include 3 baselines. The first one is prompt charm, which is a state-of-the-art prompt engineering interface for image generation. The second one is DSPy, which is an automatic prompt refinement method based on participants' textual feedback. The third baseline is clarification. It works by keep asking participants questions to better understand what they want until they stop answering questions. We also include 2 types of tasks, a closed-ended task and an open-ended task. In the closed-ended task, participants are given a target image and asked to recreate it as closely as possible. And in the open-ended task, participants can generate an image based on their own ideas. And we recorded how many iterations participants go through, as well as how much time they spend until they feel satisfied. And here are the results. In both closed and open-ended tasks, participants using Apple can get their satisfied results within a few iterations. And if we look at the time, participants were satisfied in just 40 seconds, much faster than all 3 baselines. That's because they only need to review the candidates and give simple yes or no feedback, without worrying about how to improve the prompts themselves. And we also collected users' subjective feedback with NASATX questions, and participants reported less mental demand and effort when using Apple, will they perceive their performance better than the baselines. And here are some selected results in the closed-ended task. As you can see, Apple can help participants to get results quite similar to the target images with very rough initial prompts. So to wrap up, in this paper, we present Apple, a novel method that can automatically optimize the prompts. It can infer users' preferences from their binary feedback and automatically optimize the prompt towards that. And our method is not limited to image generation. It is actually effective on any prompt-based generation tasks. We believe this work is a step toward a new form of human-AI collaboration, where AI not only translates human ideas into outputs, but also actively aligns themselves with human goals. We will open source our code soon, and we are happy to collaborate. Thank you.
Thank you so much for the great presentation. Any questions from the audience?
Yeah, thank you for your nice presentation. Very detailed work in the prompt space. In similar explorations last year at DIS and many others before, our experience was certainly what you're doing is important, but you need more clear mapping between the semantic space and image space, and without being able to express an image space, you can never reach optimum. So we can keep publishing papers, but from an optimal perspective, I don't think this one-way interaction will be sufficient. Did you notice any gaps between the image space and the expressive space that prompts, language is limited always?
Yeah, that's a very good question. So as we all know, the generation model itself is actually a black box. We never understand what kind of prompt will generate what kind of images. So it's a really good and important thing to understand the mapping between the prompt space and the image space. So like in our experience in this paper, it's like our method is really good at helping users to, like to find their desired visual style or like the image structure or something like that. But it is not very good at to have some really fine-grained improvement, such as like placing this one at the top of the table, like this corner or that corner. And this kind of thing is really bad. And it's also very hard for users to use their textual prompt to control these kind of things. So I think like, yeah, of course, we need both the improvement of the generative model itself, and we also need more research from the human part.
Thank you so much for the great presentation. And let's welcome our last presentation and also honorable mention paper. So the paper is about the envisioning and mitigating privacy risks for consumer-facing AI product concepts. And it will presented by Hank Lee. He will be on job market this year, so he's really the best person, best candidate you can consider to hire. So talk with him after the presentation.
Thank you so much. All right. Varun, thanks for the really warm introduction. Varun and I are IBM intern folks. So. All right, hi everyone. I'm Hank Lee, fourth-year PhD student at Carnegie Mellon. On behalf of my amazing collaborators, I'm excited to share Privy, an AI-assisted tool for helping product teams create high-quality privacy assessment for AI product concept. So let's begin. So today, product teams are rapidly building AI features, from facial recognition to large model-generated text, to user profiling that infer interests and demographics, right? But as these capabilities become easier to deploy, privacy risks also become easier to introduce. For example, face recognition can identify someone beyond the context expected, such as at policing. Language models can be trained on sensitive personal information like medical records, right? And user profiling can infer highly personal information people might find intrusive, such as pregnancy. At KAI 2024, we introduced the first AI privacy taxonomy, which synthesized 12 types of privacy risks, newly created or accelerated by AI, based on real-world incidents. In short, AI and intel privacy harms are not speculated. They are harming, already affecting people. And when we spoke to industry folks, practitioners building these systems, we found that they many still face barriers to even recognizing and addressing these risks in practice. So we asked, how can we design tools that can help practitioners identify and mitigate privacy risks in their AI products? And this question motivates Privy. So we begin with an initial prototype drawing from a recent HCI and AI literature on using generative AI to help practitioners surface ethical concerns. We explore how Gen AI could support an end-to-end privacy assessment decision-making process and conduct a formal study with 11 AI and privacy practitioners. Their feedback helped us to shape Privy around 4 core design goals. And here, I want to show you how these goals come to life in Privy by walking you through a quick demo of Privy in action. All right, so first, our formal study showed that practitioners' ability to identify privacy risks is grounded in understanding what the AI product does and what it requires to work. So to that end, Privy helps practitioners articulate capabilities and requirements of their AI product concept, grounded in the envisioned use cases. So in Privy, the user will first draft a description of AI product concept and provide an example use case. Privy will then help users brainstorm more intended and unintended use cases, and also help specify who will benefit from each use cases. The user can add more relevant use cases manually, or get more use case suggestions from Privy. And finally, based on these envisioned use cases, Privy help users distill the AI capabilities and corresponding requirements of their product concept. And after the scaffolding, users then go through Privacy Risk Explorer, in which Privy help practitioners identify and prioritize AI privacy risk. So Privy guides users to describe privacy risks that may arise in their product and who may be impacted. And user can manually describe the risk by referencing the AI privacy taxonomy presented on the site, or get privacy risk suggestions from preview. Then the user assess the relevancy and severity of the risk they identify. User can also review and edit their risk assessments and impact the stakeholders. Right. So through the workflow, user identify risks that are relevant and severe to their AI product concept. And finally, user rank the identified risk via this drag and drop interface in the order they think should be addressed. Indeed, the ultimate goal of identifying privacy risks is to address them. In a formal study, we found that practitioners consider risk mitigation, even identify risk. So after identifying and ranking the risk, the user then brainstorm potential mitigation strategies for the AI privacy risk they identify. So the preview interface prompts user to outline a mitigation plan for one identified risk at a time. The tool also generates open-ended questions to provoke users' risk mitigation plan specific for the privacy risks. Users are also asked to rate their confidence in their mitigation plan for each risk to encourage further reflection. And the plan is shared across the risk to allow users to build the strategies iteratively across the risks they identify. And finally, products are developed in teams, and practitioners create privacy assessment to shape how their entire team approaches privacy risk mitigation. And preview support this goal by enabling practitioners to easily compile and share findings with their teammate. And before sharing their assessments, the user can review and make final edit to the report. And the summary includes information curated through prior steps user curated using preview, such as product information, the risks they identify, and also mitigation plan they propose. And finally, each impact assessment report generated can be exported and shared with collaborators using a unique URL. Right. So to understand the role of AI assistance in the workflow, we create two versions of preview. The first is preview LM, the full LM-powered versions that provides generated assistance at each stage, as I just demoed. And the second is preview template, a static version implemented as a structured Google document with the same workflow, but without the LM assistance. We then ran a between subject study with 25 industry AI practitioners randomly assigned to either preview LM or preview template. Their task was to complete a privacy impact assessment for a predefined AI product concept that we prepared for them. We also recruited 13 privacy experts to independently evaluate the report's quality. In addition, we collected think-about data, interview data, expert evaluations, and practitioner self-reports. And here I will share a few highlights showing how preview helps practitioners produce high-quality privacy assessments for AI product concepts. First, across both versions, preview template and preview LM, preview helped practitioners identify privacy risks that were both relevant and severe. Practitioners themselves rated over 70% of the risk they identify as highly relevant and over 60% as highly severe. And practitioners' expert evaluation aligned with those assessments. Our interviews also show that preview support practitioners beyond their own privacy expertise. For example, practitioners use the generated use cases as well as the envisioned beneficiaries and exploiters of those use cases to articulate privacy risk. They also connected those risks directly to the AI system's capabilities and requirements. Preview also helped participants produce more effective and appropriate mitigation plans. Privacy expert rated these plans highly in terms of effectiveness, usefulness as a conversation starters, specificity to the product concept, and practicality. For example, participants often grounded mitigation plans in giving end user more control over their own privacy risk. Some also explicitly consider the utility and privacy trade-off, recognizing that reducing risk can sometimes limit the AI's system's usefulness. We also examined differences between Preview LLM and Preview templates privacy impact assessment quality rated by privacy experts. So both Preview LLM and Preview template produce high-quality privacy impact assessments. But when we compare the two side by side, Preview LLM significantly outperformed its static template counterpart. Reports generated with Preview LLM had risks that were more relevant, severe, correct, and clear. And their mitigation plans were more effective, specific, and practical. So in short, Preview LLM produced higher quality privacy impact assessments. All right, so returning to a key challenge I posed earlier. AI introduced new privacy risks, but practitioners are often not well equipped to address them. To what extent did Preview help solve the challenge, right? So first, Preview increased practitioners' awareness of AI privacy risk. So its structured workflow gave them clear definitions and taxonomies, which anchor their reasoning and reduce blind spots. And second, Preview increased practitioners' motivation to address those risks. Preview made privacy assessment more engaging, prompting deeper attention than they would normally give to privacy work. And third, Preview strengthened practitioners' ability to address AI privacy risk. So Preview boosted practitioners' self-efficacy. Many left feeling more confident and empowered, envision using Preview collaboratively with the product team. And we believe that these findings point to three broader design roles for integrating AI into practitioners' privacy workflow more broadly. Please see more details in the paper. All right, to conclude, Preview shows privacy assessments for practitioners can be more effective, engaging, and empowering. With that, thank you for your attention, and also I'm on the academic job market, so I would love to chat more if you think you might be hiring in human-centered AI and privacy next year. Now I'm happy to take any questions.
Thanks for the great talk. Any questions from?
Thanks, Hank. This is a really cool tool. This is Varun from Princeton. I'm curious if you've thought about generalizing this to other risks that may be applicable to AI products, because it seems like the thing which makes this like a core privacy tool is the taxonomy that you have, but the core features in terms of like suggesting use cases and coming up with mitigation strategies might be generalized to other risks, like risk from misuse or risk from malfunctions or other systemic risks. I'm curious about if you've already thought about that or ways to generalize this.
Yeah, thanks for the great question. And we have been trying to demo Preview to other industry folks, and this is one of the really common questions we got. Short answer is yes, we believe that a lot of design application can be generalizable, but sort of the more sort of nuances answer to that is, I believe that if we want to sort of doing the more generalizable approaches, as you kind of pointed out, the taxonomy itself is pretty important, right? In the sense that we don't want to just imagine LLM to kind of generate any type of risk. If we just kind of imagine it could just generate the risk that makes sense for people. So in the system itself, we kind of try to ground it pretty closely in terms of the taxonomy and also the use cases that we kind of study pretty deeply in the privacy context. But if there are other taxonomy and use cases or even benchmark from other risks that we see fit, kind of convert it into a more machine readable format, I believe that a lot of design application could be actually be generalizable. But sort of additional point onto that is, I also feel like maybe there are some, I would say, risk-specific interface design might also be considered. For example, let's say, using transparency as an example, maybe in the interface itself, in terms of the workflow that we propose in Preview, maybe some of the, for example, scaffolding of the use cases or scaffolding of the capability and requirement might be a little bit different in other type of risk, right? So I think it's just like, so short answer is yes, I believe there's a generalizability opportunity here, and also people see that, but also I think we have to, in terms of being more careful in terms of what adaptation that look like. Hope that answers your question.
Thank you so much for the great presentation and the questions. We'll wrap up the session now. Thank you for coming to the morning session at 9 a.m. and we will leave the room for your follow-up conversation after the session. Thank you. And thanks for the student volunteer.